X is X0 is non-trivial closed. Closed subspace. And X is not from X0, yes? And we have a distance, yes? Distance between X small and X0 capital is positive number D, yes? And we need to prove that there exists F X star, the norm of X equals to 1, and on subspace is 0, yes? For any, this problem.
Yes, but the value of the function in the point X is D.
Yes, but the more important information is this. You have a non-trivial functional. For non-trivial subspace, you have a functional which is 0 in this subspace. But additional information, it is a hint how to construct it. It is take this problem more easiest. But just nothing that the repeating of the first step of proving of Han-Banach theorem. So solution is following. Just again, construct the continuation on space X1, which is linear combination of element X and subspace X0. Is just all elements Y, which looks like X0 plus alpha X. X0 from subspace, alpha is arbitrary complex number. I consider every time complex situation. So by definition, by what we have just this and we have just this. So by linearity, f of y equals f of x0 plus alpha x, f x0 plus alpha fx. It is 0 by demanding it's d. It is the first step. After this, if it is not all space X, we can continue. We can construct extension due to Han-Banach theorem. But we can construct an extension only for bounded functions. So we need check that this functional is bounded. Moreover, we must check this. Yes? So let's try to do it. The norm on in X1. Here. Maybe F1, 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 and here F1, and F will be an extension on whole space. So by definition, what it means? It means supremum all over y, which is not 0, Fy over Fy. Oh. But Fy is and then, is it clear that supremum all over y's is just supremum all over x0, which is not 0, and alpha is not 0? When you change x0 and change the scalar alpha, you obtain all elements y from space x1. Yes? So supremum for all non-zero y's is just the same that supremum all over x0, which is not 0, and this is assumption. And then, can you take away alpha outside the norm? X0 over alpha plus x. What you can say about supremum of fraction with the fixed enumerator. Enumerator of this fraction is of this ratio is fixed. It's number d, and you must find the supremum of these fractions. It is just the same, minimizing the denominator. Yes? So it is just the same as d over and by definition, what is the value of this infimum? It is, this is not, this is x, but this is d. It's just the distance. It's just the distance from x to the x0. Because this element from x0 divided on alpha, it is arbitrary element from x0 capital. So that's just d. So we obtain that the d over d equals to 1. And then f is the extension by Hahn-Banach theory. So f is extension of Hahn-Banach theorem of f1. Yes? Is it clear? So remind please the second.
So we need to prove that x star is separable.
So.
Sir, before this, maybe ask about this.
Okay.
Can I take the function as the distance itself? Meaning fx equals to distance x x0, and is that a bounded function? Means that if I define f in this way,
If we write x star, it's just a bounded function.
I mean I define f equals to this x x0.
And this means that for any, this is just for any x from x0, fx equals to 0. It is annihilating on subspace. And we obtain it here. This is when we construct a 1, we just define a 1 for this term is equals to 0. And what is the question?
I mean that.
Show, please. Show. And what problems? Okay.
Define some f equals to this, and it seems that f will satisfy.
No. It is, we take some element which is not from the subspace, it exists because it's non-trivial. Then it is a definition, we define, where it is given for us. It is given for us. This is all assumptions are given for us. And then we state that there exists functional, which 0 on subspace, which is not 0, and for this, just for this element, just for this x, it equals to d. It is the same element.
So maybe I misunderstood the question itself.
Yes, it's not on the arbitrary, it's just on this element. We fixed one element, we fixed, this is one fixed element, not from subspace. Yes? Clear? We fixed one element. And on this, we have this normalization. So I take just this x. And so by definition, by assumption of the problem, we take its alpha, this is equals to d. Okay. More questions on this? No. Okay. Second, f is normed if is separable, then x is separable too. Yeah?
In this one, we should say that x is Banach space.
Yes, let's Banach. Okay, it's maybe better. But it is not, if it is not Banach, you can complete it. So, by definition, if x star is separable, what we have? by definition of separable space.
Countable and
Yes.
rule.
There exist countable set of functionals such that its completion, its closure coincide with X star. Yes? Okay, then I claim that for any k natural, there exists xk from X with unit norm the norm is a supremum on the unit sphere. So we can find the element which gives us at least the half of norm. Yes? So such elements exist. So we obtain some elements in space X. And then I consider some space X0. It's all elements X which can be given as finite linear combination of these elements xk. N is arbitrary natural. Ck are rational numbers or complex rational in real space. Or Ck equal alpha k plus I beta k, alpha k beta k are rational in complex space. What you can say about the power of this set? How large is it? Finite sum with rational coefficients.
Numero.
It is countable. Yes, it's countable. And I claim that the closure is X. We show it is countable. Let's show that it is closed. Its construction is clear. Yes? The idea. Is clear? Idea. Okay. By contradiction. By contradiction. That does not coincide with X. So what we have? We have closed, non-trivial subsequence. This is closed, non-trivial subspace. Not subsequence, but subspace. By previous problem, what we can construct? By previous problem. There exists functional fx star with unit norm which is on this subspace x equals to 0. And now we need additional element x and we need the distance. It is sufficient for our goals. The existence of such functional is sufficient. It exists due to previous problem. Yeah? So we come back again to the X star, so logic. We take some system from a dual space. By this definition of norms, we obtain some system in X. We construct some subspace in X, and then we come back to the dual space. And now use this property. What you can say about this functional f due to this this sequence? Because this sequence is dense in space, what we can
If it's dense in space, then it's dense in like every subspace of that.
we can construct subsequence.
Yes.
There exists subsequence f and k, k from 1 to infinity, such that f and k tends to f. Unfortunately, I have no place. Maybe here. Try. This is supremum on the unit sphere, yes? And this is values on some elements from the unit sphere, because x and k is subsequence of this sequence. But f acting on x and k is 0. F on x and k is 0, because f on whole space x0 is 0. So it equals to this, and this is at least half of the number of this. And we know that f and k tends to f, so the norm is continuous functions. So the norm of f and k tends to the norm of f. So it tends to the 1/2. It tends to the 1/2. What a contradiction. What is the contradiction? They are not convergent. We say that because it is dense, this subsequence must approximate our functional. But we show that this difference tends to the 1/2. So contradiction that f and k do not tend to the f. It does not approximate this element. It is a contradiction. Okay? Clear? When it is the function of bounded variations. The idea is simple if you write the pictures. If alpha, it looks like two parabolas, yes? And our function oscillates here. And if alpha, but I take, if alpha is negative, its function is not bounded. Yes? So if alpha is negative, then f is not bounded. At 0. Not on bounded variation, but just not bounded. It is necessary condition for bounded variations to be bounded, yes? So it is this interesting. And then we have such parabolas. And if we compare these pictures, where oscillation is larger? Where oscillation is larger, here or here? He is small. So then the idea that for these parameters, they are not bounded variations, and this is bounded variations. How we can show it? For this is take x and so on. And calculate variations for these points. Calculate variations only for these points. So t equals it's subdivision and calculate variation it's all over, yeah. It will be just alpha, yes. And sine in this point is -1. And this point, it is 1. So it is more correct. and alpha less or equal to 1, so this is series are not converge. So it's less to infinity. So we have no bounded variations. You see, yeah? And for this we have the same, but these points are not maximum and are not minimal, unfortunately. But we know that for so at these points, the pictures that there for these points, the graphs of function f lies on these parabolas. It's parabolas of this type. But the maximum is close, but not on parabola. And unfortunately, the equations for maximum and minimals. So you divide all interval 0, 1 on subintervals where you have monotonicity of the function. And of course, monotonicity will be between two neighbors of local extrema, between local minima and local maxima. Yes, I write a larger picture. The functions looks like here. This is here, and here we have a part of monotonicity, yes, between local minima to the neighbor's local maxima. But it is a problem to find these points because the equation for local minimum and local maximum are the following, yes? And it is equals to what? Alpha x alpha minus 1 minus yes, and if we divide it, it's look like is it right? I divide it on x powered alpha minus 1 and na cosine. And alpha is less than 1, no, less than 1, or greater than 1. And in picture you can write this it is plane T, it is tangents, graphic of tangents, and one all, so sorry, T divided on alpha, yeah? It is, looks like this line. And you see that asymptotically, this, so we have countable solutions of these equations for minima and maxima, and Tn likes asymptotically it tends to the half of pi. Is it see from picture? Yes? Asymptotically it tends to, and so we have the same series, but for not precise values, but for values which are asymptotically tends to these elements. But this is powered alpha of that less than 1. It is if alpha greater than, so sorry, if it is for this, yes? But if alpha is greater than 1, it's converged. You can say by asymptotically, it's asymptotically tends to these numbers, and you put it alpha which is greater than 1. But sorry, here plus. Here plus. Because by definition of variations, we have sum fx prime and minus x2 prime n. But in these numbers, in this one, sign is equals to minus 1. Minus 1. And here minus. So we obtain plus. So we obtain plus. So we see that for alpha less than equal to 1, it don't converge, so we have unbounded variations. But if alpha greater than alpha, the Tn tends to the local extrema tends to the numbers pi over 2 plus Pn. And this series is converged. The sum is converged. So for these parameters alpha, it is bounded variations. Is it clear? Mm-hmm. Okay. Fourth problem. Oh, the distance, yes? So the space C 0, 1 and subspace?
The subspace of function that such that the integral is 0. The integral of the function in the interval 0, 1.
For example, so-called even functions up to the middle of this interval. Yes, for example, x equals to 0.
Find the distance.
To find the distance.
Of 1 to this x.
For this function, but not previous. The next problem gives us the answer. The answer is that this is consider f capital from the dual space. It is a functional on continuous function. Then x0 is a kernel. And the answer that the distance of x0 to x0 equals to the value of this functional f capital on f0 divided on the norm of f. And for this function we have and this is less of the normal function in C0, because maximum greater or equal to the value of, at any point. So it is so the norm of the function is less than 1 or equal to 1. But if you take f identity, then f of this function equals to just to the 1. So we have here 1 and here 1. So then we obtain the distance equals to 1. But to use this, we must prove the problem 5, yes? Okay, problem 5, we use it here, yes? So we have x, we have f from x star, and we have x0, which is kernel of f. And we have some element x not from x or x star. What definition? What notation was? X star. Okay, let's be x star, which is not from the x0 distance from x0 to x star equals to the value of this functional on x star divided of the norm of this functional. But this doesn't matter, because if x star from x0, then it is 0, then distance equals to 0. The formula is valid 2. Yes? How we show, how we prove it? Two estimations, two inequalities. Two different inequalities. First inequality is very easy because by definition of kernel, you can write this equality, yes? And for this object, you can write this inequality, multiplicative inequality for the norms. And we immediately obtain what inequality? For any x0, this norm of the difference equal or larger than this ratio. Yes? I divided on this. Oh no, not on this, on this. And this is don't depend on x0. So you take infimum. Take infimum x0 and you immediately apply the distance equal or larger than this ratio, yes? This is first step. Another step, more difficult, we need to obtain inverse inequality. How we can do it? First step, I take arbitrary epsilon positive. By definition of norm, what I can construct? There exists this. Is it clear why I can do it? Because the norm is supremum, I can go to the norm, the closed, closed, and closed. So I make this smaller, and I can find the element which gives me the larger value. So then I construct new element. From this Z I construct such that f of w equals to 1. I want another normalization. I want to obtain that the value of function equals to 1. And then we obtain estimation of the norm of this w. How we can do it? Well, I think it is this element. I can divide it because it is not 0. Fz is not 0. F of z is not 0. I can divide it. What you can say about the norm of this? This is 1, this is greater or equal to this. So it is less or equal to the inverse value. Yes? Because the norm of z equals to 1. Why such normalization is convenient? Consider new element y equals to x minus this. What is the value of functional f on y? What is the value of functional f on y? Calculate, please. You know that f of w is 1. And functional is linear. 0. So y is from x0. Yes? So y is from x0. And now calculate the distance between y and x. It is just the norm of w multiplied on absolute value f of x. And we know that the norm of this less than this. So it is
Why is f of y 0?
by linearity f of x, this is number.
Yes.
F of w is 1.
1.
F of x minus f of x.
Okay.
So it is 0.
W is 1. Okay.
And epsilon is arbitrary. And this is some distance. So again, take infimum. So it is because this is infimum and this is a distance between x and some element from x0. Yes? We have this inequality. And take epsilon to the 0. Put epsilon to the 0. We obtain the inverse inequality, yes? This distance greater, and here distance less. So we have inequality. Let's discuss today problems. First problem. We have a space, Sobolev space, from -1 to 1. And we have a function which gives us the value at point ax belongs to this interval. Then we consider the symmetric situation. Symmetric situation is what situation? Ax plus, I especially takes the symmetric interval. I take symmetric interval. At 0. 0 more interesting. I state that the Sobolev space is the Hilbert space with the reproducing kernel. It has reproducing kernel. Because I remind that the Sobolev space is the function which are absolutely continuous. It is not class of equivalent functions. It's absolutely continuous function. It is good. It is better than a simple continuous function. For absolutely continuous functions, the formula, Newton-Leibniz formula is valid. You can reconstruct function over its derivatives. The integral of derivatives is the difference of values of function at the ends of the interval. It's only for absolutely continuous functions. Only for absolutely continuous functions. For example, for counter functions, you have no this property, but it is continuous function, and it has derivative of 0 almost everywhere. And derivative belongs to L2. The problem, find the norm of functional and find the reproducing kernel. Maybe inverse order. Find the reproducing kernel, then you find the norm of the functional. Find G such that f that functional equals to the scalar product with G. First, reproducing kernel, find. This is JA because it means value at point A. And reproducing kernel, it is KAB, just KGA, GB, GB, GA, this order, as we write. And for third, you can find the norm without any calculations. Because if you try to do it by definition, you must calculate the norm in Sobolev space. Norm in Sobolev space, it is integral of square function and integral of derivative function. It is not an easy problem. It's technique, but it is long. Let's, for simplicity, consider real situation because it does matter. Because in complex situation, we need to write all times the conjugation for the second term in the integral. But then we obtain some differential equations which equals to 0, and complex conjugations doesn't matter. So it is integral -1 fx g x. I don't write this index. I only write this here. Let's write. Okay. Plus primes Okay, yes? It is just a definition of scalar product in Sobolev spaces. And we want to find the function g. It exists by the Riesz theorem. So we do this. We make assumptions that these functions not have only first derivatives. Let's assume that it is have second derivatives. So we can calculate second integral by part. But we need to divide this integral into two subintegrals. I write this because the general idea, how I from integrals can obtain the value at point. By what method? By integration by parts. So, and we want to obtain the value at point A. This is f of A. So to do it, divide this integral into two integrals. Minus AA plus A1 f prime x g and integration by parts. I take away the derivatives from f on g. So it is f g a prime a minus 1 minus minus f a g minus plus f1 g prime 1a minus f a g prime a plus 0, and finally minus integral a1 f double prime double derivative dx. Look attentively. Why I write the left limits a minus 0 and a plus 0? Why we need to write this? Because the derivative is only a function from L2. It may not be continuous. It may have different limits to the left a and to the right to the a. Why here? When I work on the integral on the interval minus ya, of course I take the left limit. Yes. So here I write a minus 0, and on interval a plus 1 we have right 0. So we here write a plus. And from all these objects, you must obtain only this. You must obtain only this. What is the condition on function g? You must take away integrals. Yes? You must change it to the 0. You must take some assumptions that integrals turns to the 0. And subintegration parts at points 1 and minus 1 must be 0 too. So I take away these conditions. But what we obtain? I must that equals 0 on this interval and on this interval. We have different equations because we divide the second integral on two subintegrals, on two integrals. So this condition must be independent on each interval. Additional, we must equals 0 and this must be 0, yes? If we put these conditions, these go to the 0, and these go to the 0. And additional what assumption? What you can say about this? You can take f of a out of brackets, and you obtain that the jump at point A equals to 1 or minus 1. So this integral from a1 to f to derivative of g. It is not divided. I must just intersect.
Divided, but there are two terms. One from minus 1 to a, and one is from a to 1. Right?
This is substitution of these limits.
No, there are two integrations which include a second derivative of g.
Yes, I integrate by part, and I take a derivative from f to g.
Yes?
Yes. What question on what item you have?
I mean, the first term you integrate from a to 1. The integration.
I put this integral minus 1 integral minus 1a plus a1.
Yes, but,
And each integral I integrate by parts.
yes, but finally you sum the term, final term, and the final term, last term.
I forget the integral of plus or minus integral minus 1a f double derivative f. F. You say I omitted. Yes, I lose it. So this is right just now.
Can you sum these two terms to
Yeah, and then I divided this integral on two parts.
yes?
And I combine this with this. So this integral is integral minus 1a plus integral a1 f g. And I combine this integral with this integral, and I obtain this condition. Then I combine this integral with this integral. See? So you obtain this condition. The same equation differential, but on the second part of the integral. And then to take away these parts, I demand that these conditions fulfilled for function g. And because all this equals to f of a, so I see on this term and on this term, and I say that the jump at a of function g must be 1. So all these conditions are clear. Oh, good. How to solve it in a quick manner? What is the typical? So you have a differential equation of the second order. So the basis is two functions. What functions are typically taken in this situation? What are the bases for this? But typical are exponents. Exponents. But it is more convenient to take hyperbolic sine and hyperbolic cosine. Because hyperbolic sine and hyperbolic cosine is a linear combination of these functions. So it is another basis, and for such conditions, it is more convenient to take another solution. So I know that hyperbolic sine at 0 is 0. So I see that it is on the right side. So here I take function some number a multiplied on, and here I take function because shifted hyperbolic cosine, it is linear combinations of hyperbolic sine and cosine too. So it is another linear combination of exponents. But why is the shifted variables are useful? Because derivatives is shifted sine hyperbolic. And hyperbolic sine, when you put here -1, is hyperbolic sine at 0. It is 0. You automatically obtain this condition. And the same for this formula. The derivative is hyperbolic sine of x minus 1 and puts here, for this you put here, yes, this condition. And for this condition you put here. Is it clear? By choosing of such kind of solutions, we immediately obtain what we need. But I forget to write one additional assumption. What assumption? Your function must be from this space. So it must be absolutely continuous. Derivatives can have jumps. But somehow the functions is continuous. So additional condition is what? Additional conditions must be continuous because this. So what you can say about A capital, B capital? So it is left. In more symmetric situations, it's better to write. We know that the cosine, hyperbolic cosine, is the odd function, so we can. A is. It's more better to write this. So, at one conditions between A and B, for example, you can write that B equals to A divided on chosen on cosine hyperbolic of this argument. And now use this formula. I will take away this all because we need these calculations. We do all we can do, but we can calculate this. So derivatives A minus derivatives, it is on the left, it is on this part, and this is on this part. So what is equal to B? Can you find A capital from this? Can you find A capital from this formula? First, hyperbolic sine is an even function, yes? So I'm changing variables here and change the sign here. And you can write it's A. What you can say about formula in numerator? Do you remember the hyperbolic trigonometry rules? They are almost the same as for usual trigonometric formulas. So you can sine, cosine, sine. It is a formula of sum of sine. So it is equal this plus this. It is sine of 2. So A equals to this. So we have our kernel reproducing kernel, maybe, but not on one variable. But we have reproducing kernel for not reproducing kernel, but we have formula for GA. GA of X equals on this interval to what? A capital hyperbolic cosine. A capital equals to this. So and here we have B, and B, let's calculate B. Put this, you see that this I put this formula to this. It's a cosine, with cosine reduced. So the same, but on this cosine and how to write reproducing kernel. You take another function GB of X when A, letter A changes to letter B, and scalar product just GBGA. It depends A larger than B or B larger than A. And how find the norm of this functional? First step, but not rational step. You see this formula. You know the scalar product in the Sobolev space. You can write the integrals on this part for functions and for derivatives, and integration on this part for functions and for derivatives. But reproducing kernel allows us to obtain the answer immediately, because we know that the norm of this functional is just this by Riesz theorem. And this is scalar product and square root. And this is by definition of this function is just GA at A. And this is, you see that it equals but square root. This is the answer, without calculations and integrals. Solve the uselessness of the reproducing kernels you see here. And as A is 0, it's more simplest formula. You can put just now A0, and you can calculate the norm of the delta function in Sobolev space with negative index. Moreover, it is zero equals to something shortened. Hyperbolic cotangent over 2 and square root for A is 0. And one remark, we assume that function GA have two derivatives, but we find it. We find good function, and we know that by Riesz theorem it exists. So our approach was good. And now awful, I think, problems, because something problems tasks on convergence. First, let's consider space. Monomes. Monomes. Continuous functions. What you can say about the convergence in this space? Here we can consider only norm convergence or weak convergence, because it is not a joint space. It is not dual space. So try to understand in what sense we have a convergence here, or we have no convergence. Moreover, if you prove the strongest convergence, you immediately obtain the weaker convergence. And inverse, if you contradict the weak convergence, then you immediately contradict a strong convergence. It's some convenient remark, useful remark. From the strong convergence, you obtain weak convergence. From the non-weaker convergence, you do not have stronger convergence. So try to guess what you have here in this situation. The task, investigate it on convergence. Norm convergence or weak convergence. To contradict weak convergence, what is the weak convergence? By definitions, you must check the convergence with all functions. But for contradictions, it is sufficient to find one good functional, for which good it's broke the convergence, but it's good for us because it gives us an answer about convergence. So what good functionals you have in space of continuous function? Good and simple for calculations functionals. We know by theorem that it is Riemann-Stieltjes integral, yes, but the abstract answer is not a good object. Just concrete functionals. No ideas for concrete functionals in space of continuous functions?
It has to be not odd, right?
Functionals.
What?
You're asking why functionals?
Yes, functionals in the space of continuous functions, but simple.
An integral, no.
No. Yes, they are, by theorem, they are all integrals, but it is not convenient.
Oh, maybe the value in 1 point.
Yes, the value in 1 point. Yes, you can write it by integral, but consider the functional f sub t0 of f is the value of function f in t0. Yes, you can write it as an integral ab 0, 1 ft dg. Moreover, you know that g looks like this function, yes? It is step function, so it is a generalized derivative is delta function, but generalized derivative. But this instrument is more convenient, because if I take ft0 of fn, it is equals t0 n. And what you can say about the limit? Look attentively on the interval. Hint. It has two values. What? 0 if t0 such, and 1 is t0 equals to 1. If we have a weak convergence, it must be value of ft0 on some function f. If fn to f is continuous functions with this property exists. It must be ft0. What you can say about the continuity of such function if you have this? It is not continuous. It is not continuous. So you immediately obtain this. They are not weak convergence. They are not weak convergence. So if we have no weak convergence, what we can say about the norm convergence? There is no. There is no.
Can you repeat, Professor?
So for this sequence we have no convergence. Weak convergence
No.
and we have no, of course, non-convergence. Is it clear? Let's make this problem more difficult. The same sequence of functions, but here. But here. For, of course, for this diapason of parameters. As I write dual space, so we have three types of convergences: normed, weak, and star weak. But if I take this domain of parameters, we know that in this, for these parameters, our space is reflexive. And in this situation, weak and star weak convergence are coincide. And but Q equals to this. It is more difficult in comparison with previous problem because you need to simultaneously think about this sequence as sequence as functionals here and a sequence as function by isomorphism. First, I have isomorphism. Let's calculate the norm. It is isometric isomorphism. So I look on the function from this space, LP star, as functions from here. What is the limit as n tends to the zero, n tends to infinity, and go to the infinity?
It's two.
So we prove what? We prove norm convergence. It's converged to the zero as norm. You can write it as fn minus 0, yes? So for such p, we have convergence in norm. And if we have convergence in norm, we have what convergences? Star and weak star convergences. So the problem is that for this situation, the norm of Fn in L infinity equals to 1, because it is supremum. It continues function, so the essential supremum coincides with supremum, and it equals to 1. We have no convergence to 0, but maybe we have a convergence to some function which have norm 1. Maybe. So it is difficult to say answer here, yes? We have no convergence to 0, but maybe we have convergence to some functions with norm, with the unit norm. So let's start with the more weaker convergence. What means this convergence? Star weak. Star weak convergence for function, we consider Fn as elements L1 star. So we act by this function on the function from L1, looking on these functions as L infinity. We have the theorem without proof. But how we give this function? Fn acts on G, G belongs to L1. It's right integral Yes? What you can say about to what it's converged? Is it clear that it's converged to zero almost everywhere? Yes? It converges to zero almost everywhere. So by Lebesgue theorem, and you have majorant which belongs to L1. Is Lebesgue theorem is known? Lebesgue limit theorem? No? You have almost everywhere convergence, and they exist majorant. This. Then you can take a limit inside the integral. So you put limit inside the integral. It is Lebesgue theorem. If you have majorant, or so-called majorant theorem. And at any set except the set zero measure. Exists set of measure of zero measure. So it is where? It is for any set omega. It means that exists A, measure A is 0, and for any x on this, fnx tends to the fx. This is almost everywhere. Almost every condition doesn't imply on the integral. Lebesgue integral on any set of measure 0 equals to 0. So do you see that we have a majorant? So we can take a limit inside the integral, it is go to the 0. So we have weak convergence to what function? To zero functional. Yes, to 0. So we obtain that Fn converges to the 0. But if you want to investigate weak convergence, you must take the functionals from which space? From the second dual. You must take f from L1 2 star, because this belongs to L1 1 star, and try to say something about this. But this is L infinity star, and this is difficult object. We don't know what it. Do you understand the problem? Yes, the difficulties. We have no description of L infinity star. But if you want to broke this convergence, it's sufficient to consider one simple functional. What we can do? What you can say about all these functions? They are all continuous. Yes, they are all continuous. What I take? They all continuous, and now we consider this situation p equals to 1, so we consider it from L infinity. What we do? I take this functional ft0 of fn can I take this consider this functional in this space, in space of continuous functions? Can I consider this function in space of continuous functions? All fn are continuous, 0, 1. all these functions are continuous. Then, by Hahn-Banach theorem, we construct the extension. We construct extension of this function from C01 to L infinity 01. And by Hahn-Banach theorem, we know that all these functions are continuous. We know that these extensions equals to this, and this is gives us this. And we obtain the, if we have weak convergence, to what functional it must be? We prove that the weak convergence is to the 0, yes? So if we have have weak convergence, it must be to the 0 too. But for this functional, you see that it is not 0. And point t0 equals to 1. So we have no, again, we show that we have a weak star convergence to the 0. Yeah. Then I take this functional in space of continuous function. All these functions are continuous. I extend it to the L infinity so I can use it to this function in L infinity. P equals to 1 is just the same to look these functions from L infinity. And by Hahn-Banach theorem, it acts as for continuous function. So it gives us these values. But the limits of these values is 0 for this t0 less than 1. And 1 is t0 equals to 1. It is not equal to the 0.
So we can say that we have weak convergence only on a specific interval, and we don't have like weak convergence because of.
I take special functional. Yes. I know that if I have weak convergence only to the 0, because a weak star convergence to the 0, and I find the functional which give me not 0 values.
Exactly. So
it is not on a 0 function.
Okay, so what I was asking for, can you say that we have weak convergence on the 0 value?
Yes.
We don't have weak
Yes.
convergence. Is that
Yes.
possible?
Yes. Yes. So let's begin to write the homework. To write the next homeworks. First, let's consider this space. What means this ring? This ring means that you have boundary conditions. It is all functions from usual Sobolev space, but it is 0 on the ends. It's so-called Dirichlet boundary conditions. Dirichlet boundary conditions. It is the main space for studying of string oscillation, for example. And this condition is the fixed endpoints of this string. Due to this boundary condition, it's possible to prove that the scalar products of the form in this space is equivalent only for integrals for derivatives. It is equivalent to the full formula. The usual Sobolev space, you must write integrals for functions for derivatives. But with the Dirichlet boundary conditions, it is equivalent to the shorter formula. Only for integral for derivatives. So in this space, we always take these boundary conditions. So again, A from, and here we must take as A only from 0, 1 without including, because in this, for these points we have 0 functional. So f A of f equals f of A. First, find GA such that f of A equals, you see that it is more easier in comparison with the full Sobolev space. because in this space for such scalar product, in Sobolev we work with the hyperbolic functions. Here you must work with the splines, piecewise linear functions. I think they are more easy. Second, find the norm. Who can guess what I mean by these letters? Huh?
Alternating something.
No. It is it's analytic.
Oh.
Analytic, but with L2 norms. It's so-called Bergman space. And it is unit disk. I write this functions analytical this. Unit disk is all that. And the integral, not not complex integral, but on the plane Lebesgue measure, dx dy, and x and y is the real and imaginary parts of z. Z equals. It is a Hilbert space. It is holomorphic. It is an example of holomorphic Hilbert space, or Hilbert space with holomorphic function. Scalar product. But not dz, dz by dx dy. And here it is scalar product in this space, in Bergman space. First, is orthonormal system. It is not normal, but it is orthogonal. That's z power k. What is holomorphic function? What association you have when we hear a holomorphic function, analytical function?
What is the question? What?
How you understand the holomorphic function by yourself? You can write its Taylor expansion, for example, as power series, and it is converged on any compact. So it is you can fz write as ak z power k, and we know that it is converged uniformly on any compact in the unit disk. And from the uniform convergence, you obtain, of course, the integral convergence. So we immediately obtain that this space is complete as L2, analytical L2. Moreover, you see that if any function can be represented as sum of the powers of powers, and you check that this is orthonormal system, you immediately obtain that it is basis. Do you remember that the density and orthonormality is equivalent to the basis? So you can work with the basis, orthogonal basis. Second, consider function which gives us a point, value at point. You can again find these functions, but you can find it as sum. Just find the norm of this function. Functional. This task gives a lot of answers why, for example, in many theorems of complex analysis, we have condition functions holomorphic inside the domain and continuous up to the border. Because on the border of the domain, analytical function can be very, very bad. This functional will show you. You show that if you tend z0 to the border of the domain, the function will be unbounded. You will see if you solve this problem, the function will be unbounded on the border of the domain. And you can try to find the reproducing kernel. It is not difficult. It is a space with a reproducing kernel too. And now 3 is difficult problems, of course. Investigate on norm or weak convergence. What? Fn, it is sine. Sine P and T. It is usual sign. And for the same and 5. Do you remember these operators? Shift to the right, shift to the left, and multiplication on the sequence. Find these adjoint operators. For all these operators. Hilbert adjoint operators. And 6, integration operator. The 7 is a particular case of the 6. If you find the general answer for 6, you immediately obtain the particular answer for this particular situation. This is operator of integration. But it is very important for us, and it is good to have an answer for this operator. Not a general answer for all integration operators, a joint operator, but for this operator.